In this video, we're going to go through one more example of a limiting reactants problem before we move on to something else. So let's read through this problem. It says a potential fuel for rockets involves the reaction of pentaborane, B5H9, and O2. They react according to the following balanced chemical equation. So you've got your chemical equation there. Your two reactants are B5H9 and O2, and they're going to form boron oxide and water vapor. Just basically like a general combustion reaction that we've seen hydrocarbons do. These borohydrides can do the exact same type of reaction. It says if one tank in the rocket holds 126 grams of pentaborane and another tank holds 192 grams of oxygen, what mass of water will be produced in this process? Now, I wanted to go through this question because in it doesn't explicitly tell you to solve for the limiting reactant or determine which reactant is going to be limiting, but you'll have to know that you need to determine the limiting reactant if you're going to be able to answer a question like this, right? What mass of water is produced? If you've got two different amounts of two different reactants, then you need to know which one's going to be consumed first before you can definitively answer the question of how much water will be produced in that process. So even though it doesn't tell us determine the limiting reactant, we need to know that, okay, I need to determine the limiting reactant first before I can answer this question with any level of certainty. Okay, so let's solve for the limiting reactant. So we've been given two masses, for one for pentaborane and one for the amount of O2 that we have. So what we want to do is convert both of these guys to moles and then determine the limiting reactant. So we have 126 grams of pentaborane, so B5H9. The molar mass for B5H9 is going to be 63.12 grams of B5H9 for every 1 mole of B5H9. And so that's going to give you 2 moles of pentaborane. Okay, and for the mass of O2, we have 192 grams of O2. The molar mass of O2 is 32, so we got 32 grams of O2 for every 1 mole of O2. And that's going to give you 6.13 moles of O2. Okay, so again, these are the actual amounts that we have. I'm going to put these in a little box here. So these are the actual amounts of pentaborane and O2 that we're starting with. Right? So now we want to determine which one is going to run out first. So in order to determine this, I'm going to take the 2 moles of B5H9 and ask the question, how much O2 would it take to consume this amount of pentaborane? So if we do that, then we have 2 moles of B5H9. And we take the mole to mole ratio from our balanced chemical equation, right? So for every 2 moles of pentaborane, you got 12 moles of O2, right? So we'll have 12 moles of O2 and 2 moles B5H9. Now, again, like I said before, right, you could reduce this fraction if you want to. This is a 6-to-1 ratio, but just for the sake of these problems, I'm going to keep them the same as the stoichiometric coefficients that appear in the chemical equation. Okay, so that gives us 12 moles of O2 that is required to consume all of the pentaborane that we have. So we want to ask ourselves, do we have enough to consume all of this pentaborane? And the answer is no, right? We have 6.13 moles of O2, and it requires 12 moles to consume all of the pentaborane. So that means O2 is going to be your limiting reactant, right? This guy is going to be limiting, and that means that your B5H9 is going to be in excess. Right, you're going to have leftover B5H9 since you don't have enough O2 to consume it all. Okay, so we know that O2 is going to be our limiting reactant. So that means that we have to use the amount of the limiting reactant in order to calculate the mass of water that's going to be produced. So we're going to use the 6.13 moles of O2 to calculate the amount of H2O that's present. So first, let's get the number of moles of O2 that's going to be produced. For that, we're going to have to use the mole-to-mole ratio between O2 and H2O. So for every 9 moles of H2O, we're going to consume 12 moles of O2. So that's going to give us 4.60 moles of H2O that's produced. Now again, are we done? Absolutely not, because we need to get the mass, right? It's asking us for the mass of water, so we're going to have to use the molar mass of water to convert this number of moles to mass. So 4.60 moles of H2O, right? Our molar mass for water is going to be 18.02 grams of H2O for every 1 mole of, got that backwards. So for every 1 mole of H2O, we're going to have 18.02 grams of H2O. And so that's going to give you a final mass here of 82.89 grams of water that will be produced. Okay, so that's the mass of water that will be produced in this process. So the main reason I really wanted to go through this example, and I can't stress this enough, a lot of problems will not explicitly say determine the limiting reactant. You will need to know that if you're given 2 different amounts for each of your reactants, you're going to have to figure out which one will be consumed first before you proceed with calculating the mass of any product, right? So that's really what we did here. We weren't explicitly told determine the limiting reactant, but we knew we needed to determine that before we moved forward with the problem.